Welcome to our video of linear programming. We will first start off with explaining to you what the goal of linear programming is. Linear programming is a way of solving problems involving two variables with certain constraints in the form of inequalities. Usually we can see that linear programming problems will ask to find the minimum or maximum of a certain output dependent on the two variables. It is an optimization technique for a system of linear constraints and a linear objective function. This objective function defines the quantity to be optimized, and the goal of linear programming is to find the value of the variable that maximizes or minimizes the objective function. Linear programming can hence also be called linear optimization, as it helps find the optimal solution. Linear programming helps management learn about its maximum profit strategy or the best production programs open to it. Thus, it is a technique of selecting the best possible strategy from a number of alternatives. From an economist's point of view, this way of calculation emerges due to scarce resources in capital, personnel, equipment, material, warehousing, etc. Now, what type of problems are we even able to solve with linear programming? The basic problem linear programming answers for any manager is deciding the manner in which the limited resources can be used for profit maximization and cost minimization, as mentioned before. Operation-specific problems which can be solved with linear programming are, for example, optimizing the product mix when the production line works under certain specifications. For example, the production of two items, such as chairs and tables, with two machines which are each constrained by a certain amount of hours that they are able to run in a certain time period. Linear programming is of course not limited to this example, but can be used for many others, such as listed here. Now, what are the assumptions and properties of linear programming? When it comes to assumptions and properties, linear programming has many options. The first assumption is that there can be a number of constraints or restrictions which can be expressed in quantitative terms. The second is that the price of input and output are both constant. The third is that the relationship between the objective function and the constraints is linear. And fourth, the objective function is to be optimized by, for example, as mentioned before, making a profit maximization or a cost minimization. And the last and fifth assumption is that the parameters are subject to variation in magnitude. In addition, all linear programming problems have to follow a few characteristics. First, the characteristic mentioned is the objective function. It must clearly define an objective which can be stated in a quantitative way. The second characteristic is that the constraints, those are regarding the resources, which must be spelled out in a mathematical form. The third is non-negativity, meaning that the variables must be zero or a positive number. Fourth is linearity, which explains the relationship between the variables, which must always be linear. And the fifth characteristic is finiteness, which is related to the number of inputs and outputs, which need to be finite. Now, what are the limitations and special features of linear programming? Linear programming is important because it makes logical thinking better, and it enables us to provide better insight when it comes to business problems. So with this, managers are, as mentioned before, able to select the best solutions for them by analyzing the profit and cost of all various alternatives. The limitations of linear programming is, first of all, that the technique is not able to solve problems that are not stated in a quantitative way. Second of all, it cannot be in a non-linear nature. And thirdly, some results might be confusing and misleading as well. Further, another limitation is that there are no factors of uncertainty in this technique, and that it's difficult with this technique to clarify the objective function. Let us introduce to you now Anita. Anita has just started a business. In her shop, she sells sneakers and boots. Anita would like to maximize her profit while keeping the costs within her budget. She has a starting capital of 1,000 Swiss francs and a storage capacity of 80 pieces in total. The boots, denoted by B, will be our X, and sneakers, denoted as S, will be our Y. The costs of boots and sneakers are respectively 20 and 10 Swiss francs per unit, and the profits of boots and sneakers are respectively 8 and 5 Swiss francs per unit. From the profit, we can then derive our objective function, which maximizes the profit, Z. Now that we have our objective function, let's focus on our constraints. Our first constraint means that the total amount of boots and sneakers cannot be more than 80, as this is the maximum storage capacity Anita has. Our second constraint, which can be simplified as follows, means that the total amount of costs of boots and sneakers cannot go above 1,000 or 100 once simplified, as this is the maximum amount of capital available to her. Our third constraint means that the amount of object X which Anita buys, which are the boots, cannot be lower than 0, hence must be a positive value. The same also goes for Y, which are the sneakers. So this is our fourth constraint. To set up the graph, we start by taking the two first constraints and change the inequality sign to an equal sign, as we are going to trace the functions. Once our functions are traced, our graph will look like this. Now we can see that the two functions intersect at one point, denoted here as B, which is our corner point. There are, however, two other points we also need to consider, which belong to the common solution area in gray. Summing up, the different corner points are the following: A, B, and C. Now, if we plug these points into our objective function, for A we get 400 Swiss francs, for B we get 460 Swiss francs, and for C we get 400 Swiss francs again. Looking at the graphical results, we can see that corner point B is the most efficient solution, as it fulfills all the requirements. Anita should therefore buy 20 boots and 60 sneakers in order to maximize her profit. This is how we can solve a linear programming problem graphically. Now, let's move on to showing this example in Excel. All the necessary information is given to us by the problem formulation. We write down all the relevant costs and profits of the boots and the sneakers, being X and Y. We leave the number of units for boots and the sneakers blank, as this is what we don't know yet. This number of units, when established, will maximize our profit. Now we have the four constraints depicted, which we have previously discussed already. We put all of our constraints underneath the costs and profits. Our next step is to use the sum product formula to help with the objective function and to find the profit maximization. For the costs, profits, and each of the given constraint, we use equals sum product. Inside the sum product formula, we use the number of units for boots and sneakers. We fix these values on Excel like this, as these don't change. For example, we can put for the costs into sum product between cells C8 and D8. These are the number of units which don't change, while cells C9 to D9 are the costs for the boots and sneakers. We apply this formula onto the rest of the profits and constraints as well. Nothing appears. This brings us to the next important step, the Excel solver. We first have to set up our objective, which is the profit maximization, so we choose the cell number E10 and choose max right below. For our changing variable cells, we take our mysterious number of units. Next, we have to put the subject into the constraints. Here we have to be careful in order to separate the form of the constraints, larger equal than and smaller equal than, so we do it in two steps. To start, we take the two first constraints, which are x plus y and 2x plus y, and use the sign smaller equal than and add the cell number of the values 80 and 100. The second step has the same logic, but with the two last constraints, and this time we use the sign larger equal than and the zeros. We then click on Solve, which brings us to the solver result. Under Reports, we click on Sensitivity. We can see that in a few seconds our profit maximization and a sensitivity report appears. The sensitivity report shows you everything you need to know, from the names, the corresponding cells, to the final values of the variable cells and constraints. In our case, the sensitivity report has two sections and deals with the input, the decision variables, and the constraints. The input variable shows the use of the optimal solution. The reduced cost shows us 0, since in a two-product mix there is usually no reduced cost. It shows us how many benefits we have with each unit we make. Allowable increase, the sensitivity part of it, is how much more the profit could be per unit of increase. So in this case, Anita could increase it by more than 2 for X or decrease it by 3 for Y, and her profit would not change. The constraint section shows us how many resources Anita used, how much the optimal solution used. It shows us what an incremental increase in any of the resources would do to the objective function, and it does that while keeping everything else constant. The sensitivity analysis hence gives us insight on how the optimal solution changes. As per our result in the graphical representation of our problem, we can see that the same result has been found via the Excel way of solving Anita's problem. We hence recommend Anita that she should buy 20 boots and 60 sneakers in order to maximize her profit, and we wish her the best of luck on her endeavors as a business owner.